Hey guys, welcome back to Click Academics. In today's video, I'm going to be teaching you guys how to solve this exponential equation with, as you can see, two different bases. So what our first step is going to be is we're going to expand our right-hand side here. We have 5 to the power of x plus 2. And remember, let's say we have a to the power of b plus c. An important property of exponents is that we can change this into a to the power of b times a to the power of c. Because remember, when we're multiplying exponents, we add these two. So all we're doing is we're simply reversing this. So that's what we're going to do to 5 to the power of x plus 2. We're going to reverse it back to its original form and expand it. So 5 in this case is a, right? So we have 5 to the power of b is x, times 5 again to the power of c, which is 2. And this is still equal to 2 to the power of x. Now, 5 squared, as we all know, is 25, right? So this is 5x times 25 equals 2 to the power of x. Now what we're going to do is we're going to divide both sides by 5 to the power of x. So if we divide both sides by 5 to the power of x, well, for this side, these two will cancel out. So on our right-hand side, we'll just have 25. And on our left-hand side, we'll have 2x over 5 to the power of x. And this can actually be written as 2 over 5 whole power x. And this is equal to 25. So now what we're going to do is we're going to take the log base 2/5 of both sides. So we're going to take the log base 2/5 of both sides. Well, these two actually cancel out because remember, the log is the inverse of an exponent. So because this is base 2/5, these two are going to cancel out. So on our left-hand side, we have x equals, and on our right-hand side, we have log base 2/5 25. And this is actually equal to, using the change of base formula, which is an important property of logarithms, log 25 over log 2/5. The change of base formula states that if we have a logarithm like this, log of this equal over, so this equals log of this over the log of the base. So now this can be converted to, let me write this over here, log 5 squared, because we're simply changing the 25 to a 5 squared, over log 2 minus log 5. Remember, when we're subtracting logarithms, we divide. So we're simply just inversing that. So log 2 minus log 5. And this, an important property of logarithms, the power property, states that we can just drop down the exponent here in front of the log. So this can equal 2 log 5 over log 2 minus log 5. And this is our answer in its simplest form. If we want a more simpler form, we need to use a calculator for that, but this is the most simplest form we can write our answer in. Hey guys, welcome back to Click Academics. In today's video, I'm going to be teaching you guys how to solve this exponential equation. So we have 32 to the power of x equals 128, and we want to find the value of x. So our main objective for this equation is to change it into the form a to the power of x equals a to the power of y. So as you can see, the bases here are the same, and because the bases here are the same, that means that the exponents here are the same as well, because that must be true in order for the equation to be true. So what we need to do is we need to change 32 and 128, our bases, so that they are the same. Well, a common base for these two would be 2, right? Because 32 is 2 to the power of 5. And 128 is 2 to the power of 7. And 2 to the power of 5 would be to the power of x, because we're replacing 2 to the power of pi with 32. And this is equal to 2 to the power of 7. Now, when we have something like this, we want to multiply this. If we have this, we multiply the exponent, because 2 to the power of 5 to the power of x, so that's the same thing as 2 to the power of 5 times x. And 5 times x is 2 to the power of 5x. And this equals 2 to the power of 7 still. And now, as you can see, our bases are the same, so that means our exponents are the same as well. So this means that 5x equals 7. Now, if we divide by 5 on both sides, these two cancel out, and we get x equals 7 over 5. And this is our answer.